You're listening to MedX, the Medical Extrusion Podcast, presented by US Extruders. Extrude with confidence, custom extrusion equipment designed for you and your application.
Farhad, welcome to the MedX Podcast.
Thank you so much, Steve. It's a pleasure to be on your podcast today.
Great. I'm really looking forward to our conversation about balloon tubing and balloon forming. I think it's one of the most misunderstood concepts in medical extrusion and medtech in general, because it's a more technical process than just standard extrusion, right? And
Correct.
Hopefully we can get into some of that today, and you can share your knowledge and educate the public about it.
Sure. Looking forward to that.
Okay. Before we get into some of the performance characteristics and about balloon tubing, balloon forming, let's start by talking a little bit about the different types of balloons. I know there's different types for different applications, anatomies, and we'll get into that first before we go into a more detailed conversation. So I'll just share my screen here and let you go and talk a little bit about these three different types of balloons in biomedical.
Yeah. The balloon are categorized in three sections. One is non-compliant balloon that are made of nylon, usually nylon 12. And these balloons are basically inflated with the pressure. And how it works is that when you inflate it, you exert a pressure to break a blockage. It's called non-compliant because the diameter grow is limited. So they can only grow to about like 3 to 5% of their diameters. Semi-compliant balloon, on the other hand, is a little bit more flexible. They are made of material like P-bags. They are more flexible. And that's when you need some flexibility. So you need pressure, but at the same time, you need some kind of diameter grow. And that's where you're going to go up to like 8-10% of your diameter. Compliant balloon are made of polyurethane or silicone, and these balloons are usually when they are inflated, they are just it's just the volume that is increases. There is no pressure. Pressures pretty much stay the same, and they can increase up to 800% of their diameter basically. And the application is that when the balloon is required to conform to anatomy of that section. So basically, we can categorize the balloons into three main types: non-compliant, semi-compliant, and compliant balloon.
Okay. Thanks for that starter there. Now let's talk a little bit about some of the importance of the balloon tubing extrusion in the process.
Yeah, I would say probably the most important aspect of the balloon development process is the tube, the extrusion tube. And you know that like a tube is a precursor to the balloon. So we extrude the tube and we basically stretch that, or we blow mold it in a process where the tube would be stretched in axial and in radial direction. And we usually the tube are sized based on that expansion ratio of above 3, so between 3 to 6. Mm-hmm. And that's where like you stretch a tube in like in axial and radial 3 to 5 times larger to get to the balloon. And the engineering or science behind that expansion ratio, is in that graph that I presented here. That actually is a paper that's published in Polymer Processing that shows after the expansion ratio of 3, basically the orientation function of the molecules, they reach a plateau. Mm-hmm. On the graph on the bottom right, it shows that the orientation functions after expansion ratio of 3 or drawdown of a ratio of 3 is basically reach a plateau. So any further stretching basically is just would be decreasing the thickness of the balloon. The mechanical properties and orientation function after that, it basically reach a plateau. But the exact expansion ratio, of course, depends on the tube material and the balloon application. But that's basically the principle behind the tube sizing for the balloon application.
This is showing nylon like a semi-compliant or maybe a non-compliant, right?
Yes, this is a non-compliant nylon, basically. Okay. And it shows that after basically drawdown of ratio of 2, and that's also the same principle behind the flexible packaging, right? Flexible packaging, they stretch the nylon biaxially, and they use that in food packaging. And for that, they stretched also the stretch in nylon to a drawdown ratio above 3. Mm-hmm. And again, the science behind it is that if you stretch it beyond 3, the mechanical properties would be the same. You get your performance after 3.
Okay. For a soft compliant balloon, what are we talking about from a draw to ratio? And are we also actually stretching a compliant balloon as well, a material like a TPU? Are we doing the same type of process?
Yeah, it's the same. I mean, if you look at even the polyurethane, like a balloon, there also are segmented polymers. That means they have hard segment and they have soft segments.
Yeah, okay.
The only difference is that the ratio of the hard to soft segment is different. They have more soft segment within that structure. So it's pretty much the same principle. As I said, there is differences in the drawdown ratio, but all it lies in that range of 3 to 6. But again, depending on the exact material that you are using or application, that could change.
Okay, interesting. So let's talk about some of the factors that impact balloon performance.
Yeah. So I have tried to list all the process parameters that would impact a balloon performance here. So if we start from the resin, of course, resin is a very important part of the process. I mean, you use that to extrude your tube. And of course, the melt flow index or intrinsic viscosity of the resin, that would be, represent the molecular weight of the resin is very important. The higher molecular weight, it would be a lower MFI, or it would be like a higher intrinsic viscosity, depending if you're using nylon or P-bags. It would have an impact, right? A higher molecular weight means that, you have more entanglement density in the melt, and could potentially give you a higher strength for the final part. Resin moisture is also very important. We know that traditionally moisture would play like a softening agent for the resin, and it could impact the mechanical properties of the final part. Of course, if it gets beyond a limit, it could even disrupt your extrusion, right? Create a lot of bubbles and even stop your extrusion. But to some extent, it would allow you to extrude, and you will see the impact on the final part. On extrusion level, you have all your process parameters, right? I mean, you have your drawdown ratio at the die, your cooling system, or puller speed. All these things would impact your crystallization of the molecules. I mean, a slower crystallization or a fast crystallization could give you a different tubes that would perform differently in terms of stretchability or stiffness of the material. And of course, the tube size dimension that we already, mentioned that is a very important aspects of the extrusion side. Tube age also important. We know that for some material that have a glass transition around room temperature, over time, the properties of the material will change because of some movement that you have in the structure, in the molecular structure of the material. So they becomes a little bit more stiffer, and the stretchability would change. So that also parameters that you have to have in mind. Tube moisture is also important. The same principle. Moisture would act as a softening agent for polymers, and it could reduce the stiffness of the material, making more stretchable. And then after that would be the balloon forming process, right? The the process that you use to form the balloon, the parameters that you use for stretching, the blowing the balloons are all play a role. The balloon age also important role is not as significant as extrusion because already the molecules are oriented and are heat setted, so the movement is very limited at the balloon stage. But still, it will play a role depending where how do you store the balloon. And also the moisture, right? The moment that you open your bag is that you are exposing your balloons to moisture, depending how much relative humidity you have in that condition. And that also plays a role. So all these things together would eventually impact your balloon performance, like dimension, burst, fatigue, and compliance. The degree of the impact, it varies, right? Depending on your process, on our material, one or the, more parameters could have significant impact on your final outputs.
You talked about the quenching or cooling and the impact on crystallization. Is that a function of the gap between the exit die and the front face of the tank that determines how the crystallization and the parameters there, that die gap, we might call it?
Yeah, that's an important aspect of the process. Yes. So that distance, right, the distance between the die and the water bath, along with your pooling, when you pool, it would impact your crystallization of the material, right? It's like you are crystallizing the material faster, right? Mm-hmm. And when you crystallize the material faster, you generate smaller crystals, right? Mm-hmm. And those smaller crystals would give you a different tensile curve, a different stretchability that would play, differently when you are forming the balloon.
Okay.
So that I would say probably that's the most important process from the extrusion perspective. Probably that's the most important parameters in the performance of the balloon forming.
Okay, interesting. Is that that gap, that distance, is that something that is typically validated?
If we want to do a proper validation of the process, yes, it could be considered as one of the process parameters that that you can use in your DOE to basically validate your extrusion, depending on how do you want to design your validation process. But that definitely is a significant process parameter that would impact the performance of the extrusion process, the balloon tubing, and consequently would be the balloon performance.
Okay, excellent. Very good, very good. Let's move on to one of the very important parameters in balloon tubing and balloon forming. It's the stretchability, or you might say elongation, and I'll let you roll with it based on this very nice slide you have.
Yeah, so we mentioned that how tube sizing is important. As I said, is very important to have the right tube size for the balloon, right? To start with, right? Having the right tube size is like going from like a destination of A to B, right? For like starting from your starting point to the destination, right? Mm-hmm. And that's your tube sizing. But the way that you want to go, the path you want to go from the initiation point to the balloon is your stretchability, right? That stretchability and the stretching of the tube would, if you have a proper stretching or tensile spec for your tube, it would be a smooth ride from your tube to your balloon. Mm-hmm. That's why this tensile spec becomes important for balloon forming process. If you have the right stretchability for the tube, you will get to the balloon consistently with the same processing parameters. If you have lower stretchability, let's say your stretchability is less than what you have, what should be, you when you blow the balloon, you will get scratches. You will get especially on the cone side, you will get scratches, fish eyes, these kind of things. You are basically pushing the tubes to behave to conform it to the balloons that's not been designed for, right? So that's the aspect of the lower tensile spec. If you go too much stretchability, right? On the other side, on the other hand, if your tube is highly stretchable, then we will have problems with getting the distal neck in a spec, right? It moves too fast, and it becomes like softer basically for balloon forming process. So getting a specified tensile spec is important to get a consistent balloon forming process every time. And to do that, I've shown a tensile curve of the tube, the extrusion tube here. As you can see, so of course, we have a region of A that is elastic zone of the material. That's, when the material can be stretched and comes back on the same points, right?
Yeah.
E is your yield point, is the material yield and start to neck, right? B until C point is the necking down of the process. So when you look at the tensile of the sample, when it's stretching, you see that it's like two phases, right? One phase that is stretching, and the other phase that is the tube. So it's converting the tube to a stretch form. And the point C is that when all the tubes now is finished, is formed to the stretch tube, and a string hardening started. So basically now the tubes start, there is nothing for the tube to transition to, right? So they start now to resist to stretching, and that's why you get a slope. That slope that you have would determine this resistance of the material to stretchability. And analyzing that region from C all the way to F, that's where we can define a nice tensile spec for the tube, right? That's where we can come and we relate that to stretchability of molecular structure, basically.
Interesting. Okay. Are the tensile strength or elongation spec for different balloon types that we talked about, compliant, semi-compliant, non-compliant, is there a tolerance level within that tensile spec where you can still have consistent, repeatable balloon forming? How tight is that tolerance? Let's say for like a nylon 12, the elongation or tensile strength, how much give do you have there before you start having issues?
So depending on the application, we would like to have some points specified on tensile curves, right? For a nylon 12 specifically, so the yield point is, and the elastic modulus is not very important for the balloon forming because we already in the formation zone, right? So we are basically past point C, right?
Yeah.
So specifying probably 2 points on that region between C and F would be a good starting point, right? Like a strain at break and some points closer to C that will show, okay, now your material started to transition from necking down to string hardening. That will be a good point also to be specified as a tensile spec. The tolerance on that one, it all depends on your material, right, and your process. It's very hard to specify a specific number because there are different tube sizes and there are different tensile curves. Different tube size would give you different tensile curve, especially like a strain at break, right? The higher thickness, the higher strain at break would be. So that would be a little bit difficult to specify the tolerance. And as you get to the higher strain at break, you will get your tolerance also wider, right?
Okay.
Because now you're dealing with a higher number in the strain.
Gotcha. Wow. Very informative, Farhad. Thank you for sharing all that. I think it's important, like I said, for the market to understand the difference in some of the key technical aspects of balloon tubing versus just, a nylon 12 tube that's used on the proximal end of a delivery system in a reflow process. Big difference, right?
Yeah, it's and especially for like for manufacturer like balloon manufacturers, it's very important because it gives you a consistency, right? I mean, and efficiency in your process. Like every time you get the same kind of yield, it's consistent and also related to your like Six Sigma, right?
Yes.
I mean, you reduce your waste and it's like a smooth process instead of, getting into the try and error. Today is like 60%, tomorrow it's like 90% yield. And, all the time that you have to put into your setup and, things that that's very important to, identify the parameters that impact your outputs and then try to control them.
Okay. Thanks again. This has been a great and very informative conversation, Farhad.
Thank you so much, Steve. It was a pleasure.
All right.
Thank you for listening to MEDEX, the Medical Extrusion Podcast, presented by US Extruders. Please subscribe to make sure you're getting the latest episodes. For video episodes, go to us-extruders.com/podcasts. All links are available in the show notes.